field equations that define the magnetic field, the magnetostatics, are these versions of Maxwell's equations. The equation which shall have the no magnetic pole equation, and Ampere's law. Okay, which written in integral form say that the flux of the magnetic field through any closed surface is 0, and the circulation integral of the magnetic field around the closed contour is related to the enclosed current defined by the right-hand rule. And as we know, the integral form of Ampere's law is the thing to use to find the magnetic field if you have some special symmetry that allows you to essentially factor the magnetic field out of the integral a priori based on symmetry considerations. When we can do that, we do it. If we can't, well, we're SOL. So we have to rely on the more general solution. That general solution follows, firstly, by typically expressing the magnetic field in terms of the vector potential. And because the divergence of B is 0, that implies that that field itself is the curl of some other field. It has no component which is the gradient of a scalar, because otherwise that divergence of that would not be 0 when places where that scalar field where it's not 0. Okay. The fact that the magnetic field has this form means that there is a particular freedom we have in defining the vector potential. We can shift the vector potential to another vector field by adding to it the gradient of some scalar, because that gradient does nothing to the physical force. And that's called a gauge transformation, for reasons I don't know. When one solves problems in electromagnetics, and in this case in magnetostatics, one needs to decide what the gauge is. And what that means is we need to decide what the divergence of A is. I mean, every vector field is determined by its curl and by its divergence. But the divergence of A doesn't play any role in the physical field or the physical forces. So we can make it whatever we like, and we can shift it around by a gauge transformation. There always exists a gauge function chi, which will allow me to shift the divergence of A to the value of the field I want. And in magnetostatics, it's easiest to just set the divergence of A to 0. You don't have to do that. We just said the divergence of A is arbitrary. We can make it whatever we like. In magnetostatics, this is the easiest thing to do. In which case, the combination of Ampere's law together with the divergenceless B equation gives us a set of Poisson equations for the Cartesian components of the vector potential, and the solution is formally this, if we specify all of the currents in the problem. Okay? And you're having a lot of fun solving that for even the problem of the wires. Not but okay, so generally speaking, quite often if we have a localized current distribution, we might want to do this explicitly, either analytically or numerically integrating such a expression, but we gain important insight and important approximations under the conditions that we have a localized current distribution, and we're looking at the field far from that localized distribution by making a multipole expansion of this expression. And what we showed is, first of all, there is no monopole contribution. There's no contribution for which the potential falls off like 1 over r. There's no magnetic monopole. The first non-vanishing contribution then can be at most a dipole, magnetic dipole. And the form of the vector potential associated with the magnetic dipole moment is the magnetic dipole vector crossed into r hat over r squared. So the dipole potential falls off like 1 over r squared. Okay? The fields, of course, fall off like 1 over r cubed, just like in the electric case. And the value of the magnetic dipole moment vector is determined by this integral over the current distribution. And for the case that I have a loop of current that lies within a plane, then we showed that this vector is equal to the current times the area enclosed in that loop over C. And the direction of the magnetic dipole moment is normal to that by the right-hand rule. Okay? So the magnetic field associated with the magnetic dipole is given as the curl of the A, and we show that actually this is equal to minus the gradient of this field. How is that? I just said that the magnetic field was not the gradient of a scalar. What the heck does that mean? There it is. Well, of course, this is away from the source. Away from the source, del cross B is 0. We're in regions where J is 0. Meaning that in those regions of space, the magnetic field can be thought of as the gradient of a scalar, right? Because if the curl is 0, then it's the gradient of a scalar. It's got to be a field that's both divergenceless and curlless, but that's fine as long as we're away from the sources. And so quite often when one is solving magnetostatic problems, one writes down what's called a pseudo-potential if you're regions away from the sources, and solve the problem like you solve electrostatics problems, because those are usually much easier to do. So the form of the magnetic field associated with a magnetic dipole is exactly the same form as the electric field associated with an electric dipole. It's got this anisotropic form, and it falls off like 1 over the cube of the distance, right? Now, one last thing about this that I wanted to mention that we didn't get to last week is if we think about the case of an orbiting charge, as I say, I have some charge Q moving in some orbit, some velocity V, then, well, the current density associated with that point charge is what? QV. Well, sort of. I mean, that's, yeah, I gotta have a delta function here, right? Because remember, generally, if I have moving charge, moving velocity, this is a formula you should memorize. J is rho v. I have current, if I have charge density and it's flowing, that's the current density. But here, we have a point charge, so this is, let's say there's some position of the charge, I'll call it x of a. That's the, or x prime is a better choice. Okay? So if I wanted to calculate the magnetic dipole moment associated with this orbiting charge, because of course there's a current associated with this orbiting charge, I could do it formally, writing it down over here. The magnetic dipole moment vector associated with this is 1 over 2c, the integral d cubed. Oh, I don't like that. Sure, let me call it like that. This is my original. This is going to get confusing. What was the w variable? So that's the position of the charge. Okay, so I'm integrating over the source. J r cross jx cross into qv delta x minus xa, or 1 over 2c xa cross v times q over 2c. Okay? And we recognize this as proportional to the angular momentum of this particle, right? Because the angular momentum is the position crossed into the momentum. So if I multiply top and bottom by the mass of the particle, then this is the momentum. Position cross momentum is angular momentum, orbital angular momentum. Okay? So what we see is for a charge in motion that there is a proportionality between the magnetic dipole moment and the angular momentum. And that proportionality constant is called the gyromagnetic ratio. Okay? And what you show is that this, in fact, do we have this for homework yet? I don't think maybe we haven't yet. Oh, we did. Yeah. That this is true regardless, as long as it's not just about a point charge. Any charge distribution which has angular momentum has a magnetic dipole moment associated with it, and there's a gyromagnetic ratio which is given by the charge to mass ratio. And in fact, it is here where you know in quantum mechanics where we often call the magnetic dipole moment mu rather than m, that for a spin, the magnetic dipole moment is minus the charge of the electron times the mass of the electron over c. So it's off by a factor of 2, which is to say that the intrinsic dipole moment, say the electron, is not arising from the orbit of the particle. Because if it was, this would be the magnetic dipole moment. This is one of the clues that spin is not spinning electrons. It's an intrinsic angular momentum. It's something that's somehow intrinsic, like, attached to the electron's body that's different than the electron spinning around. And we typically mock this up by putting, say, there's a G factor for the electron times this, multiply this up by h bar, and this we call Bohr magnetism. Okay. So there's classical electrodynamics buried underneath all that stuff about spin that you kind of memorized, but you forgot what the hell the G factor meant. All right. Very good. So, now, one thing we want to look at in the same way that we did, or at least analogously to how we did in the context of electrostatics, we want to look at a multiple expansion for the forces and energies of a external magnetic field on the charge distribution. Well, of course, that's just the Lorentz force. And how do we write the Lorentz force in terms of J? We know it's QV over C cross B, right? So how does that translate into a continuous distribution? So we have the integral over the charge distribution, the current distribution. So this would be my dQV or QdV or QV over C cross into V. That's the Lorentz force. Right? If I plugged in this, you'll get Q times V over C cross V. Remember this stuff. All right, so this is the situation where what one is imagining is, there's some magnetic fields that are produced by some source. I'm not saying what that source is, but it makes some magnetic field lines. And then I have some, in here I have some current. So this is not the self-energy, this is the force acting on these moving charges due to this magnetic field, right? Is that clear what I'm showing you? Okay, so now I want to look at the case that I have a localized distribution. In that case, then I can do a Taylor series expansion of the magnetic field near the origin, assuming that the magnetic field is not varying that rapidly over the extent of this localized charge distribution. So my magnetic field as a function of x, well, it's approximated firstly by a constant, that's the lowest order, plus the first order Taylor series expansion, et cetera, et cetera. Okay? So that's just the first order Taylor series expansion of the magnetic field around this point, center of the distribution. Okay? So with that, what we see is that the force is approximately equal to 1 over C d cubed x, J of x cross into the magnetic field at 0, plus 1 over C d cubed x J of x cross into x dot L acting on D at 0 plus dot dot dot. Now, with all these vectors and cross products, we got to be extremely careful. The only way to possibly keep track of all of that is to look at the components. We'll come back to that in a moment. Because what's crossing with what in this thing? This is acting on this, but this is then crossed on the overall vector. Got to be very careful of what we're talking about. So let's look at this term first. What we showed last time is that if I have a localized charge distribution, a localized current, all the current loops close in on themselves, and this is 0. That's the effect of no magnetic monopoles. Arising from current. So the first dominant term here is this. let's look at the ith component of this force due to the, well, I'll just call it approximately equal to. So this is then equal to 1 over c epsilon I j k j I, or j, sorry, jj, jj, function of x, now dk of x. Is that clear how I chose the indices? The cross product is between this vector and this vector. So you have epsilon I j k, the jth component of the first vector, jth component of the second vector. Okay? And this then is a xl partial L. Gotta use a new dummy. All right? And then this gets evaluated at the end of the day at 0, once we've taken the derivative. Okay. So, what do I got here? I have epsilon I j k. I have 1 over c. I got p cubed x. jj xl partial L of the evaluated here. Now this we looked at last time, and in fact we said that the only thing that contributed was the antisymmetric piece of this. Which is none other than the magnetic dipole moment, right? The three independent components of this antisymmetric tensor were the three components of the magnetic dipole moment. So you remember the dual that we discussed between the vector and the antisymmetric tensor is equal if we put in LJP, we need a new index, M sub P, where M sub P, where M is 1 over 2c, d cubed x, x cross j. That's our magnetic dipole moment vector that we bring down. This is the P component thereof. Isn't this fun? All right. So, put it all together. We have epsilon I j k, epsilon L j p, M sub p, the partial respect to L of magnetic field evaluated at the center. So now we got to remember the famous contraction of two relativities. Usually this is written, you contract on, you have epsilon ijk, epsilon klm, but this is in kind of the wrong order. So let me do one of my famous asides. We're all famous now. Let's rearrange the indices, make a negative sign, but another negative sign, and that's okay. And write it as, so epsilon ijk epsilon ljp is equal to epsilon ikj epsilon jlp. So famous, follow backwards doing it. All right, so now we sum over j, it's a repeated index, and this is equal to delta IL delta KP, IL KP, yeah, minus delta IP delta KL. So put that back in to our expression for the force. And what we find is that this is approximately equal to delta IL, delta KP, minus delta IP, delta KL, MP, partial with respect to L, the magnetic fields. One of its components got lost, the K component, evaluated at the origin, or the center of the joint. Okay, so that is equal to, we sum over L, and that gives us I, we sum, so we have MP, P is equal to K, L is equal to I, or we have P is equal to I, L is equal to K. It actually worked. Amazing. What is this?
0.
Why?
This is the divergence.
Excellent. This is del dot B, which is 0. And goodbye. Nice to know you. So, what we get is that the force to lowest non-vanishing order, assuming the magnetic dipole moment is non-zero, well, this is a constant. It can come inside this, and we get partial I, NK, dk, evaluated at the origin, which is equal to, or this is the I component. The force then is equal to the gradient of n dot b. That's what we're going to have. So, a magnetic dipole, that's to say, if we have a current distribution which has a non-zero magnetic dipole moment, there is a force on that magnetic dipole due to this gradient, which could be related to minus the gradient of a potential, where that potential is minus n dot b. Of course, we are familiar with that when we, in our studies and thinking about, for example, the Zeeman effect in the hydrogen atom, and we write down the Hamiltonian associated with that, we write it as minus mu dot b, right? That's what this says, is that the lowest energy configuration is when the magnetic dipole moment is, assuming it's a positive vector, is aligned with B. And if it's not aligned, well, there's going to be a torque, right? There'll be Larmor precession of the like a gyroscope, which if I try to align a gyroscope with gravity, it precesses. That's the same dynamics that happens here. Okay? All right. Any questions about any of that? All right. So, that's magnetostatics. And I need my notes. So there's a little bit of a, there's been one, well, there's been a number of sleight of hand, but there's one in particular that you can point to. If we thought about, in electrostatics, what we said was that if we had some kind of conductor, and we place that in some external electric field, now what would happen is the charges would adjust themselves in such a way that all of the charges reside on the surface, effectively canceling the combination of these surface charges together with the external charge would make the electric field zero inside the bulk of the conductor. It would have to do that, otherwise the electrons would move. And they keep doing that until they can't move no more. Okay? Now, something is different going on when we had our magnetostatic case. If we thought about, if we have, let's say I have a rod of conductor and I connect it to a battery, we have current flowing. And it flows continuously, right? So there is something going on that's pushing the electrons. Unlike here, this came to the steady state and then the electrons stopped moving. Here the electrons are still moving. So there's something that's pushing them. There is some force on electrons inside the conductor. So this is something in some sense beyond electrostatics. Because in electrostatics, the electric field is zero inside the conductor. Well, what one finds in this kind of situation is that there's a phenomenological relationship. Between the current that's flowing and the electric field inside the conductor that's pushing them. And that relationship is known as Ohm's law, where sigma, sigma t, is the conductivity. How do we get this? Well, firstly, the current density we said was rho v. In this case, there are many charge carriers. We know them as holes because of stupid Benjamin Franklin. We got to have the positive charges moving that way, even though it's the electrons moving the other way. Thank you, founding fathers. So we have many electrons that are moving with some average velocity v, and that's what we just said was the current density. And that is the charge per unit carrier here, let's call it E, times the number density of these carriers. So this is the number plus E carriers per unit volume. All right, so we have something a little bit weird in this equation here. Remember, the force on the charge is proportional to the electric field. But we're saying that the current, we're saying that force is something like force equals something V. I thought force equals MA. How could force equal something V? Well, that's because what's going on in this situation is, I mean, if there were a constant force and that was the only thing, we know the charge will accelerate. And they would not move with a constant velocity, right? The velocity would keep increasing. That's called acceleration. But the fact that this is moving with a steady current is because the energy that's being pumped into the system is simultaneously being dissipated because there is resistance. It's futile, but there is. So, this expression, this phenomenological expression, is coming from some microscopic physics of the condensed matter system, the solid state system, perhaps. And one way we can simply model that, a very simple model of that, is by the so-called Droog model, in which case we think about the charges in the conductor as free gas, which undergoes collisions. That's really the electrons that are moving, but I'll just think about them as the holes because I don't want to have negative signs floating around. So the point is that there are some defects randomly distributed, and then there's some charge carriers which are moving around, and they hit these defects, they collide with them at some funny frequency and do a random walk. And there's some, depending upon the how the density of these defects in some sense, there's a frequency of collisions. Okay. Now, because this thing has a force applied to it, if there was no force to it, it would just undergo a random walk and it would just diffuse. But because there is a force acting on it, there will be what we call a drift velocity. That on average, even though these guys are just knocking around on the defects, the force will cause the whole thing to drift along at some velocity. So we could see that by just looking at a simple dynamical equation, which is the Droog model. Just write down the acceleration is the force, and then there's drag, and that drag is happening proportional to the velocity on average. So this is just the drag force due to these collisions. So we can then rewrite this, divide by the mass, multiply by the density of carriers and the charge, E squared N over the mass of the electric field minus nu E. potential over the ensemble. Okay? So, what we have here is an equation which can be rewritten as the rate of change of the current density moving through this conductor is equal to something which is called the plasma frequency squared divided by 4 pi, which I can find in a moment, minus nu times g, where omega p squared is 4 pi e squared n sub e over the mass of the electron. It's known as the plasma frequency, in this case squared. Everyone's seen the plasma frequency before? If you like, make it 4 pi 1 over epsilon naught, and it's maybe something that looks familiar. The plasma frequency comes in thinking about the natural oscillations of a charged gas, a plasma, which has, if you have positive and negative ions and you displace them out the mother, they will oscillate at the plasma frequency. So, this equation is called the generalized Ohm's law. Follows from the Drude model. And it's the expression that would give us generally the conductivity when we have not only have DC potentials, but AC potentials. So generally, when we'll talk about this later in the semester, we'll have J as a function of omega is sigma as a function of omega, depending upon the rate at which you're oscillating your fields. How this material responds depends on the plasma frequency and the damping rate. And so there'll be a different response function depending on that frequency. So generally, there is a frequency dependence to the conductivity. Right now, we're just talking about this quasi-static case where we have a DC field. So for the static case, J is independent of time. In which case we get a relationship here that says J is equal to omega squared over 4 pi the collision rate times V, which is the Ohm's law, where this is the conductivity. All right, now you say, that's not the Ohm's law I learned. V equals IR. What the hell are you calling this thing Ohm's law for? Well, it is the same thing. If we look at this in the context of a simple geometry where I have something like a cylinder, right, with some potential across it, and this has some thickness d, what is the electric field across this conductor? V over D, okay? We should never forget the simple thing. We don't need to write down Poisson's equation, solid boundary condition. No, this is V over D. So my electric field is V over D. If this thing has some cross-sectional area A, then the current density is the current over A. And so the Ohm's law that's written over here says that I over A is equal to sigma conductivity times V over D. Or said another way, V is equal to A over D times 1 over the conductivity, also known as the resistivity, and this quantity is the resistance, which is V. So V equals IR. All right? All right. Now, because we have resistance, what we know is that there is all of the energy that's the work that's being done here is being dissipated at once we reach steady state, because otherwise it would keep accelerating. Okay? So the power dissipated in detailed balance is equal to the rate at which work is done by the fields on the charges flowing. And that's equal to the sum over all the charges, the force on each charge. E dot F is the power, or the rate at which work is done by those forces on the moving charges. And the force is just Lorentz force. This is not a component, this is just the ith charge. This is the label that I'm just putting for the ith charge. So the magnetic fields are doing no work. It's only the electric fields, because the Lorentz force is perpendicular to the velocity. So this then is equal to sum over I, Qi, VI dotted into E at the position of the charge, or if I write it in terms of an integral, J dot E. And this, so the quantity J dot E is equal to the rate at which fields do work on charges per unit volume. And all of that work here is going into heat. And so this is sometimes called ohmic heating. Okay, but what the heck is doing this work? The work done in moving charge around the circuit well, that's just by definition that, right? Work is the force applied through a distance around the closed circuit. But what we see here is that this force cannot be due to any kind of electrostatic and or magnetostatic force. The electrostatic force we know if this was an electrostatic field, then the closed loop integral of E for electrostatics is 0. It's conservative force. On the closed loop, any energy you gain, you get back. And the magnetic field does no work. We already said that. So there's got to be something else going on. There's life beyond electrostatics and magnetostatics. It's not the whole story. We know that. In fact, in this case, that force is coming from the battery. The battery, something's going on inside the battery, which is not electrostatics, something else in this case. And this work per unit charge has a particular name. This is such sloppiness. Really name. My grandfather did. This work per unit charge of whatever the charge carrier is given a name. Also known as the EMF. Now, oomph is also known as the electromotive force, but it's not a force, it's a force per unit charge, so I don't know why it's called electromagnetic. It's got units of the potential, right? But we're stuck with oomph. All right, we gotta get some oomph. So let's think about it. Which is the famous problem of pulling a loop of wire through a magnetic field. And all of society is based on that. It's called a motor. Or a generator, or anything. So, if I have some magnetic field, let's put it into the board. All right, there it is, uniform. Magnetic fields into the board, and I have a loop. It's uniform in this region of space, and 0 outside. Here's a loop of wire. I'll put a resistance in it so it doesn't flow infinite current. And with my slimy little hand, I'm going to pull it with some force. And what's going to happen, of course, is that the free charges that are inside this wire are going to experience a Lorentz force. Which is equal to, if I'm pulling this with a constant velocity, then that Lorentz force is whatever the charge is inside here, V over C, crossed into the local magnetic field. Okay? And in this case, V is perpendicular to B, so the magnitude of this is QV over C times V. Alrighty, so if we calculate the oomph, then this is equal to V over C times B times whatever this height is, H. It's supposed to be a rectangular movement and trapezoid, but you get the picture. Okay? Now, V is the rate of change, is negative the rate of change of this distance S. And S times H, B is constant, so I can put it inside here, is the area, instantaneous area that the loop sees. And so we recognize this, if we can, through all the messy, non-perfectly erased blackboard. VSH is the instantaneous flux through the loop of the magnetic field. And so what we see, just purely from the Lorentz force, is that the oomph is equal to minus 1 over C, the rate of change of the flux of the magnetic field through that loop. Emotional EMF. Where is the oomph coming from? Of course, where it's coming from is me pulling this thing. And in fact, as I set up current, there's going to be a back action force that's going to react backwards against that current, right? And in order to keep this moving with a constant velocity, I have to keep applying force. All right. Now, finally, this example that I just sketched out here, as you've all seen from elementary studies, is easily generalized for an arbitrary loop moving through a fixed but inhomogeneous magnetic field. So more generally, I'll just do this and then we'll conclude. Pick it up later. Suppose I have some magnetic field that is non-uniform in space. In this case, it was non-uniform in a very simple way. It was everywhere uniform inside this region and then zero outside. And I have some conducting loop, or just think about it as a loop, that's moving through space somehow. Here it is at a different time. So the loop is moving with some velocity v. It's supposed to be, it's not supposed to stretch. Sorry, it's supposed to be the same loop. It's a rigid loop. Sorry. Dang. But you get it. So now the thing I want to calculate is, as this loop moves through space, what is the change in the flux of the magnetic field through that loop? Okay, that's the problem. Find the change in the magnetic flux through the rigid loop that moves with velocity v. So the way to do that is if I look at this, now let me try to draw this a little bit better. This is really kind of the same. That this, in the two different times, this loop sweeps out this little volume, right? Where the ribbon here is vt. That's the size of that ribbon as it moves. So there is a volume that is enclosed by this surface, where the bottom surface was related to the original loop. The surface up here is what the loop spans at the later time. And I can calculate what is the flux through that closed surface, including the ribbon. Okay? So what is that? Well, if I'm looking at the flux, say, out of this closed surface, then the first term is minus b dot n hat dA, where n hat was, so this is the bottom. This is the n hat according to the right-hand rule. So if I have to make an orientation for my dl. So n hat is positive here, but the n hat is negative in terms of the flux out of the surface at the bottom. Is that clear? See, let me try to draw this a little bit in a different perspective. Here's the loop. Ah, God, it's terrible. Really good. So the point is that when I calculate flux, I calculate it as all the normals out of the surface. But I want to think about it as the two loops, thinking about it with the same right-hand rule. I want to say the flux of the bottom at this time and the flux of the top at that time. Then this flux that I'm calculating for the bottom part is negative. Plus the ribbon. So I'll call this, so that, let me write this down a slightly different way. The ribbon.